A synchronous motor is one in which the rotor normally rotates at the same speed as the revolving field in the machine. The stator is similar to that of an induction machine consisting of a cylindrical iron frame with windings, usually three-phase, located in slots around the inner periphery. The difference is in the rotor, which normally contains an insulated winding connected through slip rings or other means to a source of direct current. The principle of operation of a synchronous motor can be understood by considering the stator windings to be connected to a three-phase alternating current supply. The effect of the stator current is to establish a magnetic field rotating at 120 revolutions per minute for a frequency of F Hz and for p poles. A direct current in a p-pole field winding on the rotor will also produce a magnetic field rotating at rotor speed. If the rotor speed is made equal to that of the stator field and there is no load torque, these two magnetic fields will tend to align with each other. As mechanical load is applied, the rotor slips back a number of degrees with respect to the rotating field of the stator, developing torque and continuing to be drawn around by this rotating field. The angle between the fields increases as load torque is increased. The maximum available torque is achieved when the angle by which the rotor field lags the stator field is 90 degrees. Application of more load torque will stall the motor. One advantage of the synchronous motor is that the magnetic field of the machine can be produced by the direct current in the field winding, so that the stator windings need to provide only a power component of current in phase with the applied stator voltage, i.e., the motor can operate at unity power factor. This condition minimizes the losses and heating in the stator windings. The power factor of the stator electrical input can be directly controlled by adjustment of the field current. If the field current is increased beyond the value required to provide the magnetic field, the stator current changes to include a component to compensate for this overmagnetization. The result will be a total stator current that leads the stator voltage in phase, thus providing to the power system reactive volt-amperes needed to magnetize other apparatuses connected to the system such as transformers and induction motors. Operation of a large synchronous motor at such a leading power factor may be an effective way of improving the overall power factor of the electrical loads in a manufacturing plant to avoid additional electric supply rates that may otherwise be charged for low power factor loads. Three-phase synchronous motors find their major application in industrial situations where there is a large, reasonably steady mechanical load, usually in excess of 300 kilowatts, and where the ability to operate at leading power factor is of value. Below this power level, synchronous machines are generally more expensive than induction machines. The field current may be supplied from an externally controlled rectifier through slip rings, or, in larger motors, it may be provided by a shaft-mounted rectifier with a rotating transformer or generator. A synchronous motor with only a field winding carrying a direct current would not be self-starting. At any speed other than synchronous speed, its rotor would experience an oscillating torque of zero average value as the rotating magnetic field repeatedly passes the slower-moving rotor. Normally, a short-circuited winding similar to that of an induction machine is added to the rotor to provide starting torque. The motor is started either with full or reduced stator voltage and brought up to about 95% of synchronous speed, usually with the field winding short-circuited to protect it from excessive induced voltage. The field current is then applied and the rotor pulls into synchronism with the revolving field. This additional rotor winding is usually referred to as a damper winding because of its additional property of damping out any oscillation that might be caused by sudden changes in the load on the rotor when in synchronism. Adjustment to load changes involves changes in the angle by which the rotor field lags the stator field and thus involves short-term changes in instantaneous speed. These cause currents to be induced in the damper windings, producing a torque that acts to oppose the speed change. Protection for synchronous motors is similar to that employed with large induction motors. Temperature may be sensed in both the stator and field windings and used to switch off the electric supply. Considerable heating occurs in the rotor damper winding during starting, and a timer is frequently installed to prevent repeated starts within a limited time interval.